Okay. I am recording now. Thank you. So the question I just asked the class was, can someone remind the class what the concept is behind a lithosphere? Hold on. Let me.
It's like the outer crust, right?
Say that?
It's like the outer crust.
Yeah, it's kind of like the crust.
It's a frozen brittle outer layer.
Woo! Nice. Who said that? I heard you. Nice job, young man. What's his name again? What's your name, son?
Joel.
Joel, you should be teaching this class right now. You'd be doing a much better job than I am. That's right. It's the frozen, hard, brittle outer layer. And I also liked what Jay said, believe it or not. It's kind of like the crust. That's how we want to think about it. The only difference being, of course, that you can see here in this slide, the thicknesses of the layers are not the same. The thickness of a lithosphere can plunge down maybe 300 kilometers. And that's because the crust was basically a concept based on density. It's a very low density layer. But the frozen part, the part that's crispy like a crust, actually extends down deeper into the mantle. And the reason why lithospheres matter is because lithospheres are an indicator of planetary heat. And it's going to turn out that when we talk about planets, there's two ways that we can talk about temperature. We can talk about the surface temperature of a planet, which is a factor of how close to the sun you are, what your albedo is like, and how much energy you absorb from the sun. Atmospheres can play a role for surface temperature. But today we really want to talk about planetary geology. We want to find out what makes all those bumps and wrinkles that we see on Mercury and the moon and even planets like Earth. And can we understand the history of how that happened? And that's deeply related to the inner temperature of a planet. The inner temperature of a planet is a function of several different factors, but mostly it's just how big the damn thing was when it formed, because gravity squeezing down on a rock makes it warm in the interior. And an indicator of how hot your planet is related to the depth or the thickness of its lithosphere. So let's go ahead and let's take a look at the various planets in our, actually, let's do some notes first. So let me go to speaker mode. Let me double click on myself. And what we want to do is we want to do a little lecture on planetary geology today. And we're going to be focusing on the terrestrial planets. Things that happen outside of the asteroid belt have their own psyche because of the presence of ices. Terrestrial planets are made of rock and metal, and that's what we're going to focus on today. And we're going to focus on the classic terrestrial planets: Mercury, Venus, Earth, and we're actually going to include in our discussion here the moon, because the moon is a terrestrial body of relatively large size, and we're as hungry for as many data points as we can get. And lastly, of course, Mars. In fact, I think I'd like to rearrange this now that I'm thinking about it, better. And let's rank these 5 terrestrial planets in terms of their radius. I think that's an interesting thing to do. So rather than doing their distance from the sun, as I was about to do here, let's instead rearrange this. And of course, the largest of the terrestrial planets is our planet, Earth. It has a radius of 6,400 kilometers. The next largest is our sister planet, Venus. Venus has a radius of about 6,050 kilometers. And together, Earth and Venus can be thought of as an example of, sorry, this marker's no bueno. These are examples of a large terrestrial planet, okay? So these are our large terrestrial worlds. Now, Mars is sort of like a medium-sized terrestrial planet, okay? So Mars is medium. And then we have, I think the radius of Mars is, oh, Jace, I could use your help on this, 3,400 kilometers? That's what I remember. It's 3,400 kilometers from Mars. The radius of Mercury is about 2,400 kilometers. And then lastly, we have the moon. And the moon has a radius of about 1,700 kilometers. So taken together, we can consider Mercury and the moon to be a class of small terrestrial planets. So this is sort of like Goldilocks and the three planets today. We've got big fat terrestrial planets, we've got planets that are somewhere in the middle, and we've got these little rinky-dink planets. How many of these planets have atmospheres? Students, what do you know? Which of these bad boys have atmospheres?
Was it just Earth and Venus?
And one more.
Mars?
Mars.
Yeah. So you might even want to make a note of that if you didn't know this. There's an atmosphere for these. And it's, by the way, it's no surprise that the planets with the atmospheres are the three largest. Okay. Oh, some people who join the class are actually buds of mine, so you may not recognize everyone, but that doesn't mean they're an unwelcome Zoom bomber, shall we say. My buddy Zaz likes to watch from Australia before he goes to bed, so he's out there, and my friend Catherine joins too. So I always let my friends come and sit in on the class if they want to, although I wouldn't exactly recommend this one today. Actually, we'll see if we can have some fun. There's some cool things I want to talk about. Let me go back and show you guys a picture, which is a hybrid between the different ways of looking at the interior of a planet. I'm not even saying that right. Just give me a second here. Remember that when we looked at this slide, we were comparing two different ways of layering the Earth. One way was by density, and that's the sort of classic crust-mantle core. And the other method was by strength or rigidity, where we have a brittle, solid, rigid lithosphere, a convective plastic asthenosphere, a solid mesosphere, a liquid outer core made of metal, and a solid inner core made of metal. Now, if we go to slide 21, what I thought was, yeah, here we go, slide 21. Let me go and minimize all your faces for a second. This is a hybrid picture here, which is showing us the different methods of layering the terrestrial planets by density, but it's superimposed over it a dashed black line, which is also showing you the depth of the lithosphere in each of these planets. Now let's see if we can come up with some takeaways here. The very first thing that you're supposed to notice about this picture is, to a first approximation, if you layer a planet by density, all the terrestrials kind of look the same. They all have an outer crust made of silicate rock. They have a big mantle, and then they have a metal core. Although you'll notice that the size of the metal core varies dramatically. Mercury, for some reason, has a stupidly large metal core. And kind of weirdly and suspiciously, the moon is devoid of metals. And pound for pound, its core is not proportional with its radius, but is extremely small. The moon is almost entirely rock. It has very little metal in its interior, as far as we know. Now, believe it or not, we actually set up seismographic stations when we landed on the moon. We attempted to measure moonquakes and found very little of them. There's also a current mission on Mars called the Mars InSight lander. Our most recent mission to Mars was actually a seismographic station that we landed and drilled into the lithosphere of Mars. Apparently, it's so sensitive, this seismograph, that if Mars gets pelted with small asteroids on the opposite side, the antipodal side, this InSight spacecraft can actually measure small vibrations in rock just from asteroid impacts. Nice. I like your notes there, son. Okay, so let's talk about the second and more important takeaway. Superficially, the planets all look the same in terms of crust, mantle, and core, but you'll notice that the depth of the lithosphere is not the same. Let's go and add some notes to this, and let's talk about the depth of our lithosphere. We would say that Earth and Venus are examples of planets that have very thin lithospheres. Mars has an extremely thick lithosphere, maybe about half of its radius. And although Mercury's is a little bit strange, These planets also have thick lithospheres. And this is giving us an indication of how much interior heat a planet has and how geologically active it might be. Let's take a couple extra notes here. Do you guys have this? Can I erase? Okay.
Give me 10 seconds with the bottom.
Oh, sure. Jace.
I'm guessing that hotter the interior of the planet is than the lithosphere would be, right?
I'm sorry, can you say that again? Because there was a glitch.
Sorry. I'm guessing the hotter a planet is on the side, the thinner the lithosphere would be.
This is my very next slide that I want to get to. Right. So if we're talking about interior heat, then the depth of the lithosphere indicates how much interior heat a planet has. Now, Jace, do you know what the importance of that is? Why do I want to talk about interior heat of a planet? What does that affect?
So we can estimate the heat by the thickness of the lithosphere.
Sorry?
We can estimate the heat inside the planet by the thickness of the lithosphere.
Right, but there's a reason we're interested in interior heat for a planet. It is the interior heat of a planet, that geothermal energy, that drives geological activity. And we are interested today in geological activity. So let's take a note about this, because it's going to be easy for us to kind of get these two concepts mixed up. So when we talk about planetary heat, we can think of two types of planetary heat. I'm not entirely using this term correctly, but that's okay. First, we can talk about the surface temperature. And the surface temperature at some level is ultimately caused by sunlight, solar energy heating the surface of a planet. And the factors that affect your surface temperature are your distance from the sun, something called your albedo. Your albedo is how much of the sunlight you actually absorb, whether you're a dark surface or a light reflective surface. And the third thing, which we're going to have to wait until next week to discuss because it's so insanely complicated, is the planet's atmosphere. Class, I'm assuming you already know this, but what's the hottest planet in the solar system?
Venus.
That's right. Venus is not the closest to the sun. Its atmosphere is what makes its surface hotter than Mercury. So surface temperature is one issue, and surface temperature does play a role in planetary geology on some level. But today we're going to be focusing on another aspect of planetary heat. We're going to be talking about interior temperature. And the interior heat, or the interior temperature, is what drives geology for the most part. Geological processes. The second part of our lecture today will focus on those geological processes.
What does the second asterisk say above atmosphere?
Albedo. It looks like albedo. Let me turn on my screen flip mirroring so that I can read what you guys are reading. Mirror my video. There we go. So it's A-L-B-E-D-O, albedo, or albedo. Now, I have a little slide here that talks about, well, actually, let's just go back to our picture of the planets for a second. So we can see that, according to this slide, with thin lithospheres, Earth and Venus seem to have the greatest amount of interior heat. Mars doesn't seem to have a whole bunch. Mercury is a little bit weird because its solid metal core kind of throws things off a little bit, but Mercury's lithosphere is considered thick by most planetary scientists. And the moon is basically all lithosphere. The moon is frozen rock all the way down to its core. There's almost no interior heat left there. Now I've got a cute little cartoon that sorry guys. A cute little cartoon that attempts to explain where planets get their interior heat. In fact, we're going to take some notes on this. The interior heat of a planet can come from this concept called accretion. Accretion is the heat of formation, and that means planets start out hot when they form. Then there's this important process called differentiation. The differentiated layers of Earth give it its kind of lollipop structure where there's metals in the core and rocks on the outside. And lastly, planets continue to get heating from radioactive decay of radioactive isotopes buried all within its interior. And this is an important point that is actually worthy of taking some notes. So interior heat comes from, one, accretion. And accretion basically means the heat of formation, which ultimately is coming from gravitational potential energy. So if I were to call up a little slide from the internet, if you could go back in time with your GoPro camera and film the formation of Earth, shortly after the formation of Earth, I've got a little picture here of what I imagine it might have looked like. This picture will do. Oh, this picture here, yeah. Okay, so let me share my screen with you guys. Share screen. This is a concept of what the early Earth might have looked like. Are you guys seeing my screen right now? Did I do that right? Okay. So shortly after the Earth formed, it was probably so hot, so much gravitational potential energy was released that probably the entire surface of the planet was basically molten rock. It was just warm, liquefied rock. And an early Earth, shortly after formation, it was probably glowing like a warm coal in a fire. I mean, just think about how much mass is there, and you've had to release this over a tremendous distance, squishing it all down, releasing all of that gravitational potential energy. The planets shortly after formation were probably much too hot to have any atmosphere at all. There was no liquid water on the surface. It was basically molten volcanic rock covering the surfaces of these planets. Over time, of course, the planets cool down, and then they would start to look like this. There's also a concept called the heavy bombardment period, a period in the solar system's history where many of the craters on the moon were created. And we have to deal with that at some point today too, but just hang on to your horses. Once a planet cools down and starts to look something like the surface of the moon, it still has other ways of slowly sort of maintaining this internal heat. The second, of course, being differentiation. Geologists make a big deal about the differentiated layers of a planet and how important that is. So differentiation basically means heavy metals sink and light silicate rock rises. The third method of interior heat, of course, is radioactive decay. There are radioactive isotopes all around you. In the ground rock underneath your feet, I think you smoke the equivalent of maybe 2 Marlboro cigarettes per year, whether you like it or not, just from the radioactivity that your body absorbs. Now, small amounts organisms have learned to handle. And we're not really here concerned about the effects on a person or an organism. We're interested in what does it do for a planet. These small radioactive isotopes scattered all throughout the interior of a planet can actually generate an appreciable amount of energy. I believe one of our homework problems today is going to be on this, and it's going to have a factoid for us that the Earth generates something like 30 trillion watts of internal power just from radioactive isotopes popping off. In fact, I've got a couple of cute little slides about this, if that's difficult for you guys to conceptualize. Let's have some fun with my little physics Java apps, and we'll talk a little bit about radioactive decay. Radioactive decay, of course, is part of the process of fission, where a big fat nucleus like uranium-235 or uranium-238 becomes unstable and basically breaks down, releasing gamma rays, releasing neutrons and neutrinos. If you guys can bear with me here and my S drive, I've got two cute little I've got two cute little apps here on nuclear fission that you guys might get a kick out of. This is one of them. And yes, I want to run that. Nuclear fission is starting up. Okay, so let's get that one. And there's one other one I have. Beta decay. The beta decay one is kind of cute too. Okay, so let's keep that one handy and let's go over here and let's look at a big nucleus. So here's an unstable nucleus, uranium-235. It doesn't have enough neutrons to glue it together and it's feeling a little unhappy. Let's go ahead and shoot it with our neutron gun. Uh-oh, U-236 is extremely unhappy and it basically splits the thing apart. You guys could see a release of a tiny little bit of energy in the form of gamma rays. We saw uranium split apart into two daughter nuclei. I got an idea. Let's add a whole bunch of atoms. Ooh, here's a couple. Here's some U-235. Here's some U-238. And let's just, you know, shoot this with a little neutron gun and see what happens here. Boom. Each time one of these nuclei disintegrate or whatever, they release an extra neutrons and some energy which can then collide and cascade into their neighboring atoms. U-238 is much more stable than U-235. So if you weight this with a lot of extra U-235 atoms, you can sort of get them to sort of, well actually this is the sort of secret to how we, like Homer Simpson runs a there we go, there's a nice little chain reaction. And basically this is sort of how a nuclear reactor works, right? If you guys remember Homer Simpson's job in The Simpsons, it's to sort of control the rods in the nuclear reactor here by choosing how much of the radioactive isotopes can fire neutrons into each other. So let me get your faces up here. So what we're going to do is we're going to kind of open the rods a little bit, and we're going to sort of fire off some neutrons, and we're going to generate some energy over here on the right-hand side. So let's fire the neutrons. And then Homer's job is to sort of control this slide so that we don't have a Fukushima meltdown or a Chernobyl, but we want to be able to have enough chain reaction going off so that we can generate a constant amount of power. Of course, once we're done with these rods, then we take them to Yucca Flats, New Mexico, and we dump them inside of a mountain in a big lead cavity, much to the chagrin of the local population. So, and anyways, it's a cheap form of electricity and everybody loves electricity. So inside the Earth, a similar thing is going on. Of course, there isn't quite as high a concentration. Let's see if we can find that other app now. Here we go. So somewhere inside the Earth, there are a variety of different radioactive isotopes. And these things are just, they have a certain half-life and they're constantly popping off. And all of this energy can add an appreciable amount of interior heat to a planet. Radioactive decay is an important process. Okay. Before we go forward, I think we should have another discussion. And we're going to be talking about the interiors of planets and comparing, you know, the sort of dense metal-rich core to the exterior silicate rock. What is a rock anyways? The rock, I know you guys are like, I know what a rock is, but a rock has a technical definition. Has anyone here taken a geology class so that they can tell me what the definition of a rock is? I got a little piece of granite here. What makes a rock a rock? See if we can. Anybody? Someone talk to me. Kayla, do you know what a rock is? Joel, do you know what a rock is? Chris? How about my trolls there? Emma, Samantha, Anna?
A rock is made of like gunpowder and stuff like that.
Gunpowder.
Yeah.
Well, it's
Gunpowder's a rock.
that's a pretty interesting idea, but no, not necessarily gunpowder.
You gave us a simplified definition before of like SiO2 or SiO4.
Right. So those are some of them. So I'm trying not to give away the answer here. So that's getting close to it. No one's taken a geology class and can just tell me. A rock is an aggregate of minerals. Okay. Yeah, I love that too. A rock is a really technical term. That is true, Lucas. It is. It's a technical term. It's an aggregate of minerals. So let's go ahead, and I want to share a couple of slides that I added to our show here today. If I just go back a few slides here, let's take a look at granite, like the rock that I was holding in my hand on slide 16. So granites have different composition, and I've got to say, one of the cool things about working with geologists is they just walk around and they get so excited about slabs of granite and building stone. It's kind of amazing. These little black flecks here are feldspar, and if you were to analyze a slab of granite, you might find that it's made of minerals in various concentrations. You'll notice that by far the greatest mineral composition that contributes to granite is silicon dioxide, which is kind of why I said silicon O2 or silicon O4 are the sort of classic minerals that we see. But you'll see that there's a bunch of other minerals as well, like dialuminum trioxide, dipotassium oxide. We need some chemistry friends here to remind us how to pronounce all this stuff. Chemistry is not necessarily my forte. And my way of thinking about it, what I like to think about is, what if we just took the crust of Earth and we vaporized it into pure atoms? What would we come up with? And this slide here tries to show us that. By percent weight in Earth's crust, the greatest contribution to Earth's crust is just oxygen atoms, followed secondly by silicon. So there's your silicon dioxide. And then you've got bits of metals like aluminum and iron and calcium. Sometimes I like to think of a rock as sort of like a fluffy metal. You add a whole bunch of oxygen to it, and it kind of lowers its density. And this lower density silicate rock can literally float on top of the heavier metals, the warm liquid metals that are inside the Earth. So this is a good way for us to think. Let's proceed and let's talk about two problems that planets have. One, they can get interior heat. Let's go to slide 27 here. Function F5, 27. There are three different ways to generate heat inside of a planet. And there's several different ways that heat is transferred throughout a planet. And you guys will recognize these as your three modes of heat transfer in nature. In the interior of the mantle, the warm rock undergoes convection. Remember, we talked about that rock being kind of like silly putty. It's in a solid phase, but it can flow and it convect over long time scales, geological time scales of hundreds of millions of years. When we get to the lithosphere, when we get to the solid brittle layer, we have to transfer heat through conduction, atom to atom jiggling. And that's how energy is transmitted through the lithosphere. And then eventually, when we get to the surface, we lose energy to space through radiation. Planets glow like any black body. Let's do a little sample problem on this. Okay, so planets cool down by shining light into space. And I believe if we took a planet like Earth, the global average temperature of Earth is around 15 degrees Celsius. I don't suppose any of you cats can convert that to Kelvin for me, can you? How many Kelvin is 15 degrees Celsius? Is it in the chat log? Come on, friends. Talk to me here.
288.
Yeah, you just had 273, right?
I got 288. Oh, yeah.
Yeah. Oh, 288. Isn't that what we said?
Yeah, sorry, I thought I heard you say 273.
Oh, well, 273 is the number you have to add to convert from Celsius to Kelvin. So I want to know two questions. How much light is emitted per square meter of Earth? And I also want to know the answer to the question, what is the peak wavelength emitted by this warm rock in outer space? Do you guys remember which formulas we need to answer such a question? Well, you guys are even slower on the draw than me today. No one? No one knows how to answer these questions?
Wien's law is one of them.
Yeah, which question does Wien's law answer?
Second one, right?
Yeah. And that's our peak wavelength is 3 million nanometers times kelvins divided by the temperature. How about the first one, Jace? Huh.
You remember what it's called? Square or something.
It would be B equals L over 4 pi r squared.
The inverse square law is only good if you know how much power is being, well, I guess if you use the quote that I gave you earlier, you could plug in 30 trillion watts, and you could use that, Kayla, but we're trying to do this based on temperature alone. We're considering planets cooling by shining as these are hot rocks in space.
So you'd want to use the Stefan-Boltzmann law.
That's what I'm talking about right there. So you want to use that the brightness is the Stefan-Boltzmann constant times the fourth power of temperature. So let's go ahead and let's solve those two problems for a 288 Kelvin blackbody. I'll sort of do that over here. So if we use a temperature of 288 Kelvin, the brightness emitted from Earth is 6 times 10 to the minus 8. I'll use blue here for my units. The units are watts per meter squared per Kelvin to the fourth times the fourth power of 288 Kelvin. So we have 288 Kelvin raised to the fourth power. Why don't you guys punch and crunch that for me? Well, I get a little do-rag here. I can get my calculator too. Just shout it out when you get an answer, guys. That's a you job. Talk to me, peoples.
I think the number is 413, but I'm just not sure on the units.
So you got
That's what I got too.
So we'll say 410, right? Well, you've got to distribute your fourth power to the units here as well as the number, right? The units should be pretty straightforward. You've got a Kelvin here. You got a fourth power that.
So it's watts per meter squared.
That's right. So it's 410 watts per meter squared. So every square meter has basically the power of one of those overhead transparency projector light bulbs. And what about its peak wavelength? What do you get if you do 3 million nanometers times Kelvin over 288 Kelvin.
I got 10,400
Let's just go with 10,000. 10,000 what, Jace?
nanometer.
How many microns is that, metric lovers? How many microns is that? Micrometers. What the hell's a micrometer? I thought I was talking to some enlightened students who understood the nature of the metric system.
We need Tina.
Lucas?
Is a micron hundredth of a millimeter?
Thousandth of a
Thousandth
millimeter.
of a millimeter.
Okay, so then how many microns is this?
10 million.
Oh, Jesus Christ. Look, nanometer is a billionth of a meter. A micrometer is a millionth of a meter.
So it's 10.
10 microns, thank you. In what regime of the electromagnetic spectrum are photons of 10 microns or 1,000 or 10,000 nanometers found? What band of the EM spectrum are you in?
Gamma rays?
Hell no. Do we need to
No.
call up our electromagnetic spectrum? Sounds like we do.
Like radio waves?
No, radio waves start like around a millimeter or so.
So microwaves.
Yeah, more, that might be correct. I would say probably, I'd say infrared. 10 microns is infrared. Let's see. But it could be, that could be fair to say microwave regime. Microwave regime is kind of, it's kind of messy. It's somewhere at the edge of the infrared. I'd say it's sort of smack, you know, there's different bands in the infrared. There's the near infrared, the far infrared, mid infrared. I think microwaves are a little bit closer to a millimeter. So I don't think technically microwaves would be the correct answer, but I'm a little wishy-washy on that myself. Let's say infrared. Warm rocks glow at infrared wavelengths. I don't know if this is the class where someone's got the pet lizard. One of my classes, someone has a, I think it was yesterday's class, she's got this pet lizard. This is why they like to sit on these warm rocks. They can absorb the infrared radiation and heat their bodies up. Okay, so this gets me thinking about a question that's going to come up in our homeworks today. We've got two competing factors that determine whether a planet gains heat and how it gains heat and how it shines it away into space. And let me explain what I'm talking about with some notes here. Class, can I erase this? Has everyone caught up to me? Okay. Oh, you have the lizard? All right, Matthew. I think someone in my yesterday's class does as well. Okay, so imagine we're going to talk about something that a planetary scientist, in your book, they call it the surface area to volume ratio. But my version of doing it is I like to do instead the volume to surface area ratio of a planet. And believe it or not, this is kind of a thing in planetary science. It's one of the ways that people analyze how geologically active a planet can be. Imagine I have a sphere, and the sphere has some radius r. And spheres, of course, have volumes. The volume of a sphere is 4/3 pi r cubed. A planet that has more volume, a bigger planet, is going to have released more gravitational potential energy during its formation. It will undergo more differentiation, and it will hide more radioactive isotopes buried in its interior that contribute to the interior heat flowing through a planet. So in a weird way, the volume of a planet is sort of proportional to its heat holding capacity. On the other hand, larger planets also have more surface area. And the surface area of a sphere is 4 pi r squared. We just analyzed that a planet will emit something like 400 watts per square meter from every square meter panel on its surface. 400 watts per square meter, radiating at about 10 microns. And of course, the bigger your planet is, the more square meter panels you're going to have on its surface to shine away that light. And therefore, the surface area can be thought of as being proportional to the cooling rate of a planet. So the question is, how are these two things going to compete with each other? Both volume and surface area scale with radius. As a planet gets bigger, which one of these things is going to grow faster, the volume or the surface area?
Volume.
Sorry, Jace?
Is it volume?
Yeah. Why?
Always grows faster than surface area.
Right, but I was hoping you could sort of explain it in terms of our formulae here. Does anyone get what I'm driving at here? Or I must not be making. I'm sorry.
Is it because the radius is
Is it
cubed in the
hours?
formula?
Yeah, it's about the powers. Yes, it's about the cube dependence, right? The cube is stronger than the square. And sometimes people will try to sort of make this explicit by taking something called the volume to surface area ratio of a planet. And the volume to surface area ratio of a planet is an indicator of how much internal heat it can hold. So the volume to surface area ratio, if you do 4/3 pi r cubed over 4 pi r squared, 4's and pi's cancel, and 2 of your radii cancel, and you get 1/3 r. And this means that the volume to surface area ratio of a planet is directly proportional to its radius. Let me spell that out for you in case you aren't quite following what I'm doing here. This means bigger planets stay hotter longer than small ones. Class, what does that have to do with this picture? Hold on. What's that have to do with this picture? Does anyone get my point?
Yeah, the lithosphere, the cold outer layer, is smaller on the bigger planets.
That's right. This is why Earth and Venus have thin lithospheres and are geologically active. This is why the Moon and Mercury are basically cratered rocks in space with no atmosphere. They've lost all of their interior heat. Mars is kind of a weird story. In next week's lab, and maybe even a little bit today, I'm going to show you pictures of the surfaces of these planets. And Mars is very interesting because it started off a lot like Earth. It had an atmosphere, had oceans at one point, it had volcanism, maybe even a tiny bit of tectonics. But Mars cooled off a lot faster than Earth did during the 5 billion years that our solar system has been sitting around. And over time, this kind of thickened up the lithosphere, like day-old pizza. And eventually it became so hard and so thick that no more interior heat was left to ooze through the cracks. And over time, Mars slowly started to die. Let me show you another picture, a picture that I think is kind of interesting. I'm going to show you a grayscale map of several planets in our inner solar system. And I need this slideshow here.
If you were standing on the surface of Mercury, though, wouldn't the air temperature be so much warmer than it would on Earth?
Oh, remember, we don't want to confuse surface temperature with interior temperature, Lucas. First
But
of all,
the
okay,
planet doesn't absorb any of that heat.
no. Okay, wait. Here, let's look at a picture of Mercury. I've got a picture for you here. Just a moment, buddy. Okay. Mercury does not have an atmosphere, right, Lucas? When we think of warm or cold, we tend to think of the temperature of the air. But if you're standing on the surface of Mercury, there are two possible temperatures. There's the subsolar side where the radiation is beating down on the rock, and the temperature of that rock is 700 Kelvin. That's probably hot enough to melt lead, all right? On the dark side, on the nighttime side, it's 100 Kelvin above absolute zero. But remember, if you were standing on the surface of Mercury, Lucas, it's just the vacuum of space. You wouldn't feel particularly warm. Well, if the radiation was beating down on you, you probably wouldn't like that very much. But when we're talking about the surface temperature of a planet, you'd have to imagine taking off your space glove and laying your hand down on the rock. That's what is meant by the surface being warm. So there's no atmosphere to speak of whatsoever to absorb any of that radiation. Now, Mercury has a very slow rotation. I think it's, I don't know, 60 days or something. So yeah, somewhere along the terminator on the boundary between daytime and nighttime, there might be some sort of intermediate temperature, but there's no such thing as a pleasant day on Mercury, no matter where you are, right? Whether you're on the nighttime side or the daytime side, it's not going to be a lot of fun. And this light basically just gets re-radiated right back into space. But that's, of course, not exactly what we're talking about, right, Lucas? It's the interior. The sunlight doesn't penetrate down into the planet. There's some interior temperature that leaks out through the surface. I don't know. Lucas, I don't know if that answered your question.
Yeah, no, it did. I was just wondering if its proximity to the sun, since the sun is so hot and it's so much closer, if it just heated the whole thing, but obviously not.
Yeah, well, remember, as soon as this rock rotates into the antipodal side, or whatever you want to call it, the side that's not facing the sun, that light is radiating out into space, and the rock just cools off right away, right? It's absorbing some of the sunlight and immediately scattering and re-radiating it back into space. Anyways, I'm not making any sense today, guys. You got to put up with me. Let me show you some interesting slides since my words are no good. I want to show you a picture of surfaces of 3 different planets and see if you can guess the planet. Now, there's no reason you should know which planet we're looking at, but that's just part of the game. So here's a grayscale image of a planetary surface. This is one of our terrestrial planets. Take a guess which one it is. Anyone want to hazard a guess as to which planetary surface we're looking at?
Venus?
That is correct. Was that a guess, or did you have some reason to know this?
I just didn't see any craters.
Yes, this is a key point, Lucas. This is the point that I'm trying to make. All right, let me show you another grayscale planetary surface. What are we looking at now? This should be obvious, right?
Earth.
As soon as you see this, you know you're looking at Earth. And what was the tell? What was the giveaway?
The continental shapes.
Yeah, the shapes of the continents. And that's an indication of the major differences in geological activity between Earth and Venus. You don't see those perfectly sculpted continents. I mean, okay, you can see there's some little mountains here. There's some stuff, but it's not like these big epic continents that poke right off of the surface. What geological process would you say is responsible for these continental land masses? If you had to associate the continents with one type of geology, what would it be? No? You can't tell me?
Tectonics?
Yeah, plate tectonics. This is a stark reminder of Earth's active plate tectonics. Things like plate tectonics are driven by the interior heat of a planet. All right, let's do one more. What am I looking at?
Is that the moon?
It's not the moon. There's too much craziness in this for the moon. It certainly looks like the moon down here, doesn't it?
Mars?
That's Mars. But Mars does look in some ways like the moon, and this is one of the points that I'm trying to make. What is the first thing, the first global distinction that you recognize between Venus, Earth, and then Mars? What does Mars have that these guys don't have?
Craters?
Yeah. This surface
Only
is
on one
pockmarked
side, though.
in the southern hemisphere. Yeah, this is an interesting point. We're going to do a whole lab using the Mars MOLA, the laser altimeter data. I have this beautiful map of Mars. Oh man, I sure hope I stole that. Actually, it's online, so we don't have to worry about that. We're going to do a lab where we basically poke our way through the surface of Mars and talk about its geological history. That should be a really fun lab for us next Monday. But the first thing that you notice when you look at Mars, which makes it different than Venus and what makes it different than Earth, is suddenly the introduction of just thousands and thousands of craters all over its surface. And yes, they are primarily based in the southern hemisphere, although you can see a few in the northern hemisphere as well. This means something. This means that Mars, at some point, maybe it could have been cool like Earth. It could have had interesting geology, like these giant volcanoes and this epic chasm called the Valles Marineris. But over time, Mars is slowly turning into something that resembles more like the surface of Mercury or the moon. Craters are an indication of a dead planetary surface, a surface that does not have active geology. And it's funny, I mean, am I supposed to imagine that all of those meteoroids flying through space just happened to hit Mars and happened to hit the moon and they somehow missed Earth? Did all those impacts miss Venus? I mean, it's kind of a funny thing to think about, right? Here's Earth and the moon are floating in space, right? And somehow all of those impacts just all hit the moon and they missed Earth. That's why we can't see any of their evidence today. That's certainly not, that's not realistic. It's not realistic to think that way. In any case, you could see that the size of a planet correlates with what types of interesting geology we see on its surface. And now it's time for us to discuss those types of geology. This will be our final thing that we do for the day. So I want to address something called the 4 geological processes. And we're going to kind of break down planetary geology into 4 modes that kind of describe what kind of surface features we see on a planet. I don't know if I'll be able to get through all 4 of them, but I'll give you sort of little brief descriptions to help us understand. Now that we know that interior heat is what's driving geology, we can focus on the geology itself. And if we want to use something like Aristotle's sculptor analogy, we can think of the 4 geological processes as sort of like sculptors. And these sculptors basically shape the surface of a planet over time, and they are responsible for why Mars looks like it does or why Earth looks like it does today. Sorry, I've lost focus here. 4 geological. So these are sculptors. And they are, in no particular order, impact cratering, volcanism, plate tectonics. While we see tectonic features on all planets, a complete set of robust plate tectonics, we want to make a note of this right away, is basically unique to Earth. Earth's surface, as you can see from those continental land masses, is dramatically shaped by the process of plate tectonics. And no other planet has such a robust version of this geological process. And lastly, the all-important erosion. Now, I've got some words to say about each of these things. We're going to start with impact cratering because it's going to come up in our homeworks today. Let's make sure that you guys get this stuff down. back to the slides for a moment. Let me show you some fun pictures. Guys, can you help keep me, when I start talking about impact cratering, I get a little bit excited. So in 15 minutes or so, remind me that we need to end class, okay? Let me just show you a few slides before that happens. Share screen. Let's go to, wait a minute, did I do this right? Yeah. Share screen. Let's go ahead and look at a model of how impact craters are formed, okay? Now, if we go and we look at the surface of the moon is just completely riddled with impacts all over its surface. And as I was mentioning before, one of the things we'd like to ask ourselves is, why do we see such an abundance of craters on Mercury and on the moon, and so few on Venus, so few on Earth? And Mars is kind of a half. First of all, does anyone already know the answer? I mean, do you guys know why Venus and Earth don't have any impacts?
Does it have something to do with the atmospheres?
The atmospheres actually, the atmospheres block small meteoroids, but not large ones. Actually, maybe let's do this before we do anything else. I want to bring up 3 terms and see if you guys know the difference. There is a meteoroid. There is a meteor, and then there's a meteorite. I don't suppose anyone knows the difference between these 3 things. Like simple one-word description. A meteoroid is when the rock is in space, okay? The meteor, the fireball, is when it strikes the atmosphere. And then the meteorite is basically when it's on the ground. So that's the rock that's left over. Now, space rocks, meteoroids, can have several different origins. Some of them are broken off pieces of asteroids, or maybe an entire asteroid in itself. Others are pieces of rock that are broken off of planets. Some of the, I think maybe 20% of all the meteorites found on Earth are identical to the surface composition of Mars. And they're rocks that seem to have been blasted off the surface of Mars. So they can be parts of comets. Comets contain loose piles of rubble and rock at their nuclei, and they kind of get scattered in an ellipse around the sun. When Earth crashes into them, we get our meteor showers. But in general, we can just say meteoroid is a blanket term to talk about rocks that are coming from space. Now, I have a picture. Hold on here, share screen. There's a slide that I want to share with you guys. And I want to show you guys a slide that addresses the question, how often does Earth get hit with a meteoroid? Asking the question, how often does Earth get hit, doesn't actually make sense. You have to ask it in the following way. How often does Earth get hit with a rock of size X? So let me go to slide 109 and explain what I mean there. This tries to show the frequency with which Earth today is struck by meteoroids from space. So every hour of every day, we get struck with a 1 meter sized boulder from space. And I'll remind you guys that a meter is pretty big, right? A human being is 2 meters tall approximately. And yes, Lucas, things of that scale size, a meter or so, do kind of dissolve and burn up in our atmosphere as a giant fireball and are just vaporized into dust. But as soon as you get to about 10 meters, which we get struck with every year or so, those things are capable of making it to the ground and creating small craters or powerful atmospheric explosions. Every 1,000 years to every 1,000,000 years, you might get hit with a big boy, something 1 kilometer in size, and that's capable of wiping out some dinosaurs, causing climate change, making giant tsunamis. And maybe every 100 million years, maybe every 1,000,000,000 years or so, a few times in Earth's history, you get hit with the real big boy. This is something bigger than 10 kilometers. And that's sort of game over for most organisms on Earth. That's a mass extinction sized object. You'll notice, Lucas, that only the smallest little pebbles and rocks are capable of being burned up in the atmosphere of Earth. So just saying, oh, it's because Earth has an atmosphere is not sufficient to explain why Earth is not riddled or pebbled with all of these massive impacts. Do you guys remember in our labs last week, we had to measure and estimate the size of the crater Tycho? We did that, right? How big did Tycho turn out to be? You guys have those notes handy? And Tycho was sort of a garden variety.
Is the reason we don't hear about meteorites because most of them just land in the ocean if they are big enough to make it all the way through?
Yeah, but we do hear about them. Oh man, there's so much cool stuff for me to share with you guys. Let's watch this video I'm not gonna have time to talk about all the aspects of this I want to today. There's a cool video on YouTube of meteor filmed by a police camera in Canada. And there's several different examples of this. But I want you guys to watch this. This police camera filmed a meteor striking the sky over Canada. And this was probably a rock that was big enough to actually make it to the ground and create a small crater. Although there's a lot of forest up there. But just bear with me and just watch this video for a second, okay? So that bright fireball that you see there is called a bolide. They're going to do it in slow motion. Notice that the frictional heat creating that fireball, it's so bright that it turns the nighttime sky into daylight. So Lucas, I wouldn't say that we don't notice these things happening. They're captured all the time in cameras. I don't know if you guys remember. Actually, there was one that happened right over Rhode Island last summer. Did anyone actually get to see that? A whole bunch of my students started texting me on Saturday night, and they said, Brennan, I saw a giant bright light in the sky. I think I saw a meteor. And I was like, nah, I think you were drinking, you know? I was like, are you drunk? Don't text me when you're drunk. All right, because then I'm going to start texting you when I'm drunk, and it's going to be a mess. And so I thought they were making fun of me or something. And then sure enough, I go into work the next day, and I get a call from Channel 10. It's like, this is Brian Crandall from Channel 10. Are you available to talk about the meteor that struck last night? I went, oh, damn it. And so I had to race down to my office and start doing some research to find some footage of this thing. So Lucas, these things happen all the time. There was one that struck Russia a couple of years ago that a whole bunch of people caught a meteor over Russia. This thing blew the glass out of a bunch of windows. People got all sorts of different views of this thing. Here's someone from Russia today. Here's your talking head here. So look at that video there. Look at this thing. Look at that fireball. It's amazing. I don't know if you guys understand the point I'm trying to make here, but Earth is getting struck with meteoroids from space all the time. And no, it's not that we don't notice it happening. If you live long enough and you kind of pay attention to these things, people are constantly finding these things. By the way, I could show you a couple other slides here. Here's a little time-lapse indication of, and there's a reason I want to show this to you as well. A good rule of thumb for meteor impacts is that the crater that's left behind is anywhere from 10 times to 100 times bigger than the diameter of the impactor. So you shouldn't get the concept, you shouldn't think that, oh, if I see a crater of this size here, then the rock that made it must have been exactly the same size. It doesn't work like that. These things have tremendous amount of kinetic energies when they're plunging down into Earth. I have a sample problem on this, but I don't know if we're gonna have time to do it. Typically, meteoroids and rocks in space are traveling anywhere from 10 kilometers per second to 15 kilometers per second. And they've got a big chunk of rock and metal associated with them. The kinetic energy is capable of vaporizing a massive crater 10 to 100 times the diameter of the impactor. Now, I asked you guys to look up the size of that crater Tycho. Let's see if I can find it. Did anyone, so that was HR Astro Waxing Gibbous. Do you guys remember what Tycho looks like? Let me show you this picture of the moon again.
Are you sure we measured the diameter of Tycho?
I'm pretty sure, yeah.
We measured Pluto.
Pardon? Oh, I'm sorry. I did this last week too. I'm sorry. This is crater Plato. What the hell? Tycho is the one that's up. I believe this is crater Tycho up here with the central peak. I did this last week too. I'm so sorry. What about this guy? What about crater Plato? Thank you, Kayla. How big is that puppy?
90 kilometers.
90 kilometers. That's longer than the state of Rhode Island. And we don't just see one crater like this. The point of measuring that is there are impacts all over the surface of the moon of that size. We don't see this stuff on Earth. It's incredibly rare. Let me show you an example of where we do see it on Earth. I was fortunate enough to have gone to college in Arizona, and one of the coolest things that you can take a little trip out into the desert to see is a giant impact site called Meteor Crater. And I want to show you a picture of this. Actually, it's on private property. It's owned on this dude ranch, and the crater is about 1 mile in diameter or so. Here's a picture of it from, yeah. Well, let's, hold on a second, guys. Let's find a large image here. Bear with me, I'm trying to do something. Tools, size, large. Okay. So what I remember from when I went out and saw this thing is meteor craters on private property, and you have to drive for hours and hours and hours into the eastern Badlands of Arizona. And I went out here one spring break. This crater is on a dude ranch on private property. So after you drive up the highway, you have to pay $20 to look at the impact crater, and they make you walk through this really tacky gift shop in a corrugated tin shack that has like I love UFO keychains and like, you know, alien t-shirts and stuff like that. And you pay your money and you walk through the gift shop, and then you stand at the edge of this thing and you think, holy shit, imagine what that would have been like being here when this impactor struck. They actually trained some of the Apollo astronauts in here, since they were going to send these guys, you know, to the moon, and there were going to be many, many impact craters significantly larger than this. They thought maybe we ought to put you in a spacesuit and have you crawl around inside this thing and see if that works for you before you get up there on the moon, right? So, and I can tell you, when I stood at the edge of this thing, scrambling down it looked like a whole damn day hike. Yeah, Jace.
How come there's no central peak?
That's a great question. How come there's no central peak? The answer to that question, Jace, rather than just telling it to you, I want to show you another crater. This one from down under in Australia. It's known as the Wolf Creek Crater. Oops, I spelled it wrong. Let's take a peek at Wolf Creek Crater. See, things like this are not things that you see every day. You'll notice that Wolf Creek Crater also does not have a central peak. How would you compare the appearance of Wolf Creek impact crater to Meteor Crater?
This is way more shallow.
Yeah. Oh, by the way, you know, if we wanted to get technical about these things, and you know we do, we could diagram parts of a crater. Some terms here. Craters tend to have a rim, okay? The bowl that's excavated is called the basin, okay? This is the basin. As Jace was mentioning, sometimes they have a central peak. And then oftentimes craters would be surrounded by a blanket of, sometimes we call it ejecta. That's the material that it spits out. Sometimes when they're coming out like this, remember we call those rays. So there's a little diagram of a sort of model of an impact crater. Now, Jace is asking about the central peak. Guys, if you were asked without any special training to compare Wolf Creek Crater to Meteor Crater, could you tell me which one is the younger and which one is the older crater? Would you be able to do that just on an instinct? Is this the older crater, or is this the older crater?
Wolf Creek is older.
Yeah, how do you know Wolf Creek is older?
It seems like it's like eroded.
Yeah, it's eroded. The basin has been filled in. The rim has deteriorated and worn down from wind erosion, probably from water erosion, storms. I mean, does that answer your question of why we don't have a central peak? Earth has active geology that is constantly changing its surface. The continents are being pushed around due to plate tectonics, and the lithospheric plates are smashing into each other. Volcanoes are erupting that repave the surfaces with lava. And of course, erosion is nonstop, happening everywhere. Erosion doesn't happen on the moon because the moon doesn't have an atmosphere. It doesn't have any moonquakes. It doesn't have any volcanoes spewing lava over its surface. Hell, if you look at the surface of Mars, you can kind of see what happens right there. Mars topographical map. I think we
Are
must
those
be
even
getting
close enough to being big enough to like screw with the Earth's axis tilt?
probably in the early solar system, yes. Today, unless you get hit, you'd have to get hit by a stupidly large object for that to happen. So not today, but probably in the early solar system was a violent place. Let me do one more little lecture notes with you today. You know, the rate or the frequency with which impactors strike Earth and the other planets today is roughly the same. And you guys looked at it in this slideshow, in this slideshow here. So when I showed you slide 109, the frequency with which meteoroids strike Earth and the moon, this is basically what it looks like for planets today, but it was not like this in the past. And that's because of how planets formed. Let me just use Wikipedia here instead of hunting around for slides, and let's look up something called the heavy bombardment period. If you could go back in time to the early solar system would have been a messy and violent place, full of not just small little tiny meteoroids, but giant Mars-sized asteroids, things we called planetesimals that were raining and smashing down onto the surfaces of the planets. We believe one of the reasons why Earth has such a large moon is because Earth must have gotten struck earlier in its history by a Mars-sized planetesimal. Yes, Lucas, that would definitely affect your axis tilt. Although gravitational perturbations can affect them over time, planets probably did get knocked around quite a bit. In the case of the Earth, we believe its crust was torn off and that the moon is actually a bit of Earth crust and a bit of the thing that struck Earth that kind of tore off the surface of Earth and eventually solidified into a moon. When you look at the surfaces of a planet like Mercury, and you see just all of these crazy crater on top of crater on top of crater, most likely these craters that just pig pile on top of each other, most of them were formed during the heavy bombardment period. This is a history of just how violent the earlier solar system must have been. Unlike Earth and Mars, which have powerful erosional forces and plate tectonics and things to erase their craters, Mercury and the Moon have no atmosphere and not much active geology, and they bear a history of the violence of the early solar system. So if we were going to define the heavy bombardment period, it's a period in the solar system's history during the first 1 billion years where massive planetesimals must have rained down onto its surface. And people actually have gotten quite technical about the time periods. So they have an early heavy bombardment and a late heavy bombardment. And this is anywhere from 4.1 to 3.8 billion years ago. The idea is that this is supposed to explain the difference in the two types of surfaces that we have on the moon. If you go and look at lunar maria, the surfaces of the lunar maria are quite smooth, whereas the highlands are covered in impact craters. And so a question that planetary scientists were trying to address is, okay, why are the surfaces of the maria so smooth and then the highlands just ripped to shreds by impacts? It must have been that there was this violent history of the solar system where massive impactors rained down on the surfaces of the planets. And then after that, somehow these giant pools and lakes of lava must have formed on the moon. The basic moral of the story, the whole point that I was trying to make, can be summed up in two little points, and then we'll move on to your homework. So the first point is that all planets get hit with meteoroids. However, not all planet surfaces show evidence of cratering. Therefore, if you follow this to its logical conclusion, as a planetary scientist, you can use the density of impact craters as an indicator of the surface age of a planet. The density of impacts indicates the surface age of your planet. And we'll be making use of this next week. And obviously, more impacts implies an old surface, one that's been sitting around getting pelted over time, and fewer impacts or no impacts indicates a young planetary surface. So impact cratering from a planetary science point of view is a really excellent indicator of the history of what happened to a planet over time. Okay. Class, I think I've used up my allotted time and then some with you guys. Sorry this lecture wasn't as smooth as I wanted it to be today. What do you say we stop the recording, take a little pause, and then we crank out our homework? Our homework is going to be directly related to the stuff that you guys were just learning there. Any questions or comments before I get some more iced tea? Okay. So let's stop the recording.